The work energy theorem, it's called the work energy theorem because it's going to relate work and energy. It's really, really useful. First of all, we need to remember what was energy. Energy was the ability to do work. Now, how do I find work? Don't write this next bit down. Zaina, we said work was force times distance, which was the easiest way to find work, but it had its limitations. The force had to be constant, and the force and distance had to be in the same direction. This won't help us in Physics 12 when we start doing rocket science, because when you want to figure out how much work, how much energy, say, to put something in orbit, gravity is changing as you go further and further away. This won't help. We also said that work was the area, don't write this down, underneath a force versus distance graph. And as long as the area was a fairly easy one to find, that was okay. But what if it's a curve? And by the way, that's a sketch of the graph of gravitational force as you leave the Earth. It is a curve. You don't know how to find the area underneath the curve. Those of you who are doing calculus next year, one of the skills you'll learn in calculus near the end of the year is you can use calculus to find the area underneath the curve, but I can't assume you have that. So Eric, here's the best definition of work, but it's also the most writing. Work is triangle PE. What does that triangle in a brief for, Zaina? Change in plus change in kinetic. If you want to know how much work you've done on an object, measure its change in potential energy and its change in kinetic energy. Oh, and what's change in anything? It's on your green sheet, top left corner. What's change in anything? Final minus initial. Okay? I only use this definition of work as my last resort. In other words, if I look at example 1, it says this. A cyclist weighs 65 kilograms, her bike weighs 7.2 kilograms. You know what? Let's just make a note. The total mass then is 72.2 kilograms. That's what we're going to use for our mass. If she's pedaling over level ground, Cole, what's this asking me to find? How much what? Work does it take for her to increase her speed from rest to 5 meters per second? Don't write this next bit down. Look up. This is how my brain would do this. What does it want me to find? How much what? My first thought would be, well, maybe work is force times distance. Do you see a force in newtons here anywhere? Do you see a distance in meters here anywhere? So I would probably mentally scratch that out. Then I might be tempted to say, hey, it's also the area underneath the graph. Cole, be obvious. Did they give me a graph? Then I go to my third definition of work. Write this down. Work is the change in potential plus the change in kinetic. When would gravitational potential energy change? When there is a change in, I'm looking for a word that starts letter H. You good, Scott? Oh, you need the eraser because you wrote it down when I said don't write this down? I liked you better with the longer hair. Yeah, okay. Oh, and on cue. Okay. Sorry. Cole, when would there be a change in potential energy? When there's a change in? That would be a change in kinetic energy. When would there be a change in potential energy? When there's a change in, I'm looking for the starts letter H. Height. What word is that? Is there a change in height in this question? Okay. If there was, I would include it. Don't need it. What's change in anything? This is going to be a half m v final squared minus a half m the initial squared. Oh, in this question, Cole, what's VI as a number exactly? So what's my initial kinetic energy as a number exactly? So I could have probably done that if I'd really been paying attention, but I wanted to write it out just so you could see how it all fits together. And now I can tell you how much work for this cyclist to increase her speed from 0 to 5. It's going to be 0.5 times m times 5. Don't forget the squared. And I got 902.5, double check me. You want to type this because then you can backspace and edit shortly and do some quicker stuff. Is that right? 902.5? Work, joules. Cole, one last question. By how much did we increase our speed if we went from 0 to 5? By how much did we increase our speed by? 5 meters per second. Is that all right? Okay. Eric, in part B, by how much are we increasing our speed by? Shouldn't it be the same answer? It will not be. It wants us to find how much work. We would walk through the same procedure. I would first say it's force times distance. Did they give me a force or a distance? You'll say. So then I would say maybe it's an area under a graph. They didn't give me a graph. I would say work equals the change in potential plus the change in kinetic. Are we still over level ground? So it's going to be the change in kinetic. What's change in anything? So this is what I would write down. Work equals a half mv final squared minus a half mv initial squared. It's going to be 0.5 times 72.2 times 10 squared minus 0.5 times 72.2 times 5 squared. You're not going to get 902.5 even though it's the same 5 meter per second increase. In fact, 2707.5? Double check me. Is it 2707.5? The faster you go, the more work it takes for the same increase. See it? In fact, by how much are we increasing in part C? 5. But I'm going to tell you that 5 meter per second increase in part C is not going to be 2,707.5. We can walk through the same argument. I think it's going to end up being a half mv final squared minus a half mv initial squared. It's going to be 0.5 times 72.2 times 15 squared minus 0.5 times 72.2 times 10 squared. In fact, I'm willing to bet if you have a good calculator, you might be able to just backspace and edit and change the 10 to a 15 and change the 5 to a 10. And you're going to get an even bigger answer. I think something in the 4,000s? But that's about as much as I can do. Aiden, what'd you get? 4,512.5? Sorry, what was it? 4,000? Joules. What does this mean? So this is important because it affects all of you once you start paying for gas yourself. The faster you go, the worse your gas mileage. See it? More energy is required. More work is required. Where's that energy coming from? Fuel. Fuel. You're about to start driving over the next few years, and I hope you don't become one of the idiot drivers. I see them all the time on the low heat. It's classic. I commute home to Abbotsford, so I'm on the low heat heading during rush hour into downtown Maple Ridge. And I'll see someone come blazing past me, zipping in and out through traffic, weaving in and out through traffic, and they vanish. And then at the next red light, I catch up to them. And then the light turns green, and they go zipping off through traffic, in and out through traffic, and they vanish. And do you know when I catch up to them again? At the next red light. And they keep doing that. They are burning this much energy, like way more energy than necessary to get to the same place in the same time. I mean, I kind of get it if you're on the Coquihalla and there's no red lights, and you know by driving faster you can reduce time on the road. But understand, by doing that, you're burning way more fuel than if you were just driving smart. But you may decide that your time is worth it. But the people that do it in city driving are just stupid. I mean, how many times am I going to catch up to the same idiot before they figure it out? Don't be one of those. Does that make sense? Next page over. You can use this for rocket science. Fahim, it says this: a model rocket reaches a height of 340 meters when launched if the top speed of the rocket is 85 meters per second. Ooh. Fahim, what's this asking me to find? How much work the rocket engine did. In other words, how much energy did the rocket engine supply to this? Now, my first thought, don't write this down, Scott. My first thought would be to go work equals force times distance. However, I mean, I kind of thought since there's a height, maybe the force is mg. But if I did that, would I be using that 85 that they gave me at all? No. So I'm thinking I'm going to use the work energy theorem. The fact that it's the change in potential plus change in kinetic. Fahim, is there a change in the height this time? Then that's not going to cancel out. The change in potential won't cancel out. Is there also a change in speed? Yes. So unfortunately, I can't just cross out entire terms. So let's expand this. Fahim, what's change in anything? Say it again. So this is going to be PE final minus PE initial, and then there's a plus sign. And then KE final minus KE initial. Someone's going to make sure their phone's on vibrate. Let's look at potential energy. When is gravitational potential energy zero? When we're on the ground. Fahim, are we ever on the ground in this question? When? Initial or final? So I can at least do that. Kinetic energy is zero when we're at rest. Fahim, are we ever at rest in this question? When? We're starting out on the ground 1 second before launch. You can kind of think of that, as they say, as T minus 1. So that's zero as well. Now, you'll notice I didn't say the final speed of the rocket is the top speed, because I know it's going to start to slow down, and come to a stop. But I do know at one point it had that much kinetic energy. I had whatever a half mv squared is. And now we can expand this. Work equals mgh final plus a half mv final squared. How much energy did this engine have to supply to get this rocket this high and this fast? M 0.15, G 9.8, H 340, plus 0.5 times M 0.15, V 85, don't forget the squared. What do you get? Fahim, let me know what you get. Probably not that big an answer. I don't think. Fahim didn't like his answer, so he's trying again. Yeah. 941.7. Anybody else? I don't think that's right. Aiden, what'd you get? I don't think, is that right? 1,041? Is that right? 1,041 units? Joules. So, is that correct? I haven't seen much. Yeah, okay. Yeah. Oh, 42? So if we round off properly, Aiden, is it 42? I'll do that, and that way no one will know. That's how much chemical energy minimum had to be stored in that rocket. Now, you saw the rocket launch. It also gave off a lot of sound and smoke and heat. That would also be coming from the gunpowder, so there'd have to be more energy than that, but at least that. Is that okay? Good. I like example 3. I like example 3. Example 3 is a nice question. A car is traveling at 35 meters per second over level ground. Cohen, what's A asking me to find? Again, don't write this down, Scott. My first thought would be force times distance. Do you see a force in this question? In newtons. Do you see a distance in this question? It's also the area under a force versus distance graph. Did they give us a graph? What's our third definition of work? Oh, did I give you that definition on your green formula sheet? I hope I did. Is the work energy theorem on your green formula sheet? This is my way of saying, can you all make sure you know where it is so you're not going, oh. Yeah. Sorry? More specific. What's the equation? Can you read to me the two words after the word over? What does that mean? I gotta be fussy. The change in potential is 0. No change in height. What's change in anything? So this is going to be a half mv final squared minus a half mv initial squared. Are any of these 0? I'll give you a hint, Cohen. Yes, one of them is. Which one? Why? Because Aiden said so? Why? Read me in part A after the word to. A stop, you say? Okay. So I'm going to get this. How much work to bring this car to a stop? Negative 0.5 m v squared. What do you get? You're going to get a negative answer. We'll talk about what that's telling us in just a second. Do you get negative 765,625? Why negative? Well, it's telling me the car has to lose energy. Okay? Has to lose energy. Where does that energy go? It's got to go somewhere. Where does it go? Yeah. Heating up your brakes, mostly. Oh, unless, who has an electric car? Okay? One of the many reasons electric cars are so much more efficient is this energy, we don't bleed it off as heat. We bleed it off as electrical energy to recharge the battery. And because we're bleeding off energy, cars got to slow down. Have to. Losing kinetic energy, we're just saying, why send it to heat? Send it to somewhere useful. I have a friend who has an electric vehicle, and coming down the Coquihalla, he ended up at the bottom of the mountain with more energy than he had at the top. More charge in his battery than he'd had at the top. It was recharging on the way down. We were turning potential energy into electrical energy. B. Clody, what's B want me to find? Force. Don't write this down, look up. I would have no problem if you went F equals what? MA. There is enough information there for you to figure out A. VF is 0. VI is 35. D is 82. I think you can use VF squared equals VI squared plus 280. And I'm fine with that. But let's see if we can get there a little quicker. What did we find in part A? There isn't a version of work that has force in it, is there? Can you get the F by itself, please? It's going to be negative 765,625 divided by 82. And I get negative 9,300 and, if I round off properly, Aiden, 40. And, oh, it's a force, Clody, units. What's the negative telling me? If the car is going forwards, the force has to be pointing. If the car is going north, the force must be pointing. The opposite of north, which starts with letter S and rhymes with outh. If the car is going north, the force must be pointing. If the car is going east, the force must be pointing west. Okay. Okay. So that negative there is telling me something a little useful about the direction. What's creating the force? What force is bringing a car to a stop? Friction. Ooh, if we were on ice and we still had to get rid of this much energy, but the force couldn't be as big, what has to be bigger? Distance. That's why you have to take further distance to stop on ice. Yeah, of course. That makes sense. But there's the physics of why. Ooh, Maddie, what's C want me to find? Well, I just decided that that was the force of friction. That's what's bringing it to a stop. What's another way to write friction? Friction is what times what? I think I would start out by writing friction equals mu times the normal force. What do they want me to find? What's that in this equation? Hey, what's mu? I don't know. What's mu? How would I get the mu by itself? I know friction. I'm going to write 9,340. I'm going to chuck the negative now because mu is a scalar and no units. So I'm just going to assume that they just want a magnitude anyways. There's no direction here anyhow. I'm going to use my answer button though. Divided by, I don't know the normal force. Can you imagine the free body diagram? How big would the normal force be the same size as? Yeah. I think level ground mg. I'm going to be brave and go straight to my calculator. So it's going to be, I'm going to multiply by -1 to get rid of the negative. And then it's going to be answer button divided by bracket 1250 times 9.8. And I get 0.762. Units for coefficient of friction. Oh, it has none. It's the weird one. Oh yeah, that makes sense. It would be newtons divided by newtons. The newtons would cancel. So this is the work energy theorem. When do I use it? If force times distance doesn't work, and if they didn't give me a graph. Okay, turn the page. Finally, I promised you way back when, at the beginning of kinematics, we did a question like this. We looked at an RCMP crash site investigation, and we calculated the speed. But Eric, I had to have a cell phone have picked up the sound of the skid, which is a really dumb coincidence that would never happen in real life. And I promised you then, once you learn enough physics, actually, you can get there just from the distance and measuring the coefficient of friction at that site. Here it is. RCMP are investigating an accident. Car struck a pedestrian at a school crosswalk. There are no witnesses to the accident, and the pedestrian either, sadly, didn't make it or can't remember the accident. The officer measures the coefficient of friction at the accident site to be 0.65. They have a little device that they drag, and they can figure that out. And it measures skid marks that are 49 meters long. Should the RCMP press charges? So here's my question. What's this asking me to find? Charges? No. In terms of physics, what's this question asking me to find? Yes, Sophie? Oh, I thought that was a hand up. Sorry. My bad. Cohen. Which one? Because what's VF of any car accident ever? Okay. So I'm just going to make a little note here. That's what they're asking me to find. Now, Mika, I don't think I'm going to ask you one this tough on your test. In your homework or on a quiz, this will be fair game. And I'm going to start out making maybe the most obvious statement that you can make. I'm going to say, don't argue with me, work equals work. Booyah! I realize that's right up there with saying 5 equals 5. But actually now I'm going to write both of our primary definitions for work. One way to write work is force times distance. Another way to write work is change in potential energy plus change in kinetic energy. Is there any hint in this question that we're on a hill? Is there any hint in this question there's a change in height? Now, if I gave this to you on a test, physics 12 maybe, but not physics 11, I would have said something like, we're on level ground or something like that. But you can see, by the way, even in real life, if we're not on level ground, we just measure the change in height, we can plug it in there, we're still good to go. So RCMP, or whoever's investigating the crash, they can handle that. The road does not have to be flat. Everybody, what's change in anything? That was not everybody. Everybody, what's change in anything? Mika didn't move. So everybody, what's change in anything? Mika Sid didn't move. Everybody, what's change in anything? Jada hasn't moved your lips. What's change in anything? So I guess this is going to be force times distance equals a half m v final, don't forget the squared, minus a half m v initial, don't forget the squared. Oh, Cohen, what did you say v final was? And I'm going to do one more thing. Maddie, you notice on the right-hand side it is negative? See the negative? Technically, I should have put a negative there because the force and the distance are in opposite directions. And now what I'm going to say is actually the negatives are going to cancel the rest of the way. We can ignore them. What are we trying to find? Oh! Get that by itself. Okay, we can do that. What's going to drop down like a domino? Good. The negatives will cancel. What do I do with this 1/2? I'm going to times by 2 and divide by 1. But will dividing by 1 make a difference, Cole? Am I going to bother writing it? No. How will I move the m over? And that equals VI squared. Finish it off. How'd I get rid of a squared? Okay. Cool. Which force? Yeah, I could have put a little friction right there. It's going to be the force of friction. That's what's bringing the car to a stop. Do I know the force of friction in newtons? No. Oh. Friction, Aiden, is what times what? I think my next line, I would write VI equals the square root of 2 normal force, mu normal force d over m. I don't know the normal force. Well, if I visualize the free body diagram, what's the normal force the same size as, Aiden? I think I can say this. VI equals the square root of 2 mu mgd over m. Oh! Is there an m on the top? Is there an m on the bottom? More specific, is there an m in everything on the top of that mini fraction? Is there an m in everything on the bottom? See what happens to the m's? What does that mean? In real life, it means even if the police don't know the type of vehicle that was involved in the crash, they can still, Eric, start the investigation and go along. They don't need the mass of the car at this point, which is kind of handy. Now I think we can crunch this. It's going to be 2, what's mu? I don't know what's mu with you. 0.65 times 9.8 times 49. What do you get? You get 24.9. You know what? I think no matter how I round that off to 3 or 4 sig figs, it's going to be 25.0, I think. 25. Is that right? Should this person be charged? How fast is that in meters per second? How fast is that in meters per second? Anyone? Zayna, what'd you get? 89? In a school zone? Probably going to get charged. So we've gone one step further with our car crash investigation from having to have the cell phone fluke and record the sound of the skid. I promised you once you learned more, we don't even need that. Ooh. I need to show you somebody being really, really dumb. Don't try this at home. So this is a motorcycle from Vancouver Island, and I took it because I can see the speedometer right here. This person is driving very dumb. They posted this on YouTube, and they were very dumb. Why are we looking at the sky right now? Dumb.
I'll see you tomorrow, okay?
Have an awesome day.
Okay.
How fast are we going? I think that's 210. So, 220 what? Units. I look here, and I see, there's 90. I see 3 digits there. This is miles per hour, not kilometers per hour. 320 miles per hour. Dumb. Part A. Let's jot down some data. VI is 320 miles per hour. How fast is that? Convert 320 miles per hour to kilometers per hour.
That was
Sorry, 220. I said 320. 220. You're right. You're right. I apologize. I'm getting too ahead of myself. Convert 220 miles per hour to kilometers per hour.
It's 354.06 kilometers per hour.
We're going to convert it to meters per second. I just did the kilometers per hour to let you know you have not seen anything going that fast. This was from about 2006, 2007, which is why the resolution is so lousy. But this idiot posted this on his YouTube channel. And of course, the RCMP saw this from Vancouver Island, and they were on him. They confiscated his bike because this is driving unbelievably unsafe. Convert 220 miles per hour to meters per second.
On it.
I know you are. A little quicker, please, Siri.
It's 98.35 meters per second.
98.4. And now this driver, oh, wrong button, is going to start to slow down. What's VF in miles per hour? Those of you at the front can read. 100. Okay. Convert 100 miles per hour to meters per second.
The answer is 44.7 meters per second.
All right, we got some data. Ella, what's A asking me to find? How much energy is lost? You know what? I think what it's asking me to find is the change in energy, the work using the work energy theorem. So I'm going to go like this. Work equals change in potential plus change in kinetic. Change in potential occurs when there's a change in height. You saw the video. Did that road look like it had any hills? I think we can safely say that. Looked pretty level. What's change in anything? So I guess this is going to be a half mv final squared minus a half mv initial squared. When this story broke way back when, newspapers covered it, and somewhere some article mentioned what kind of bike it was, so I looked up its mass, and then I added an average mass of the rider because I didn't know the rider's mass. So this 300 here, I'll bet you I'm within 20 kilograms plus or minus. I'm close at least. So we're going to use that as our mass. The amount of work is going to be 0.5 times 300 times V final is 44.7 squared minus 0.5 times 300 times 98.4. By the way, that 220 miles per hour, 98.4 meters per second, like, that's a football field a second. I don't know if you remember, yesterday we calculated the speed of a slingshot, and it ended up being 60. That rider would be passing the slingshot. A couple of days ago, I think we calculated the speed of an arrow, and I think that was in the 80s. This rider is faster than a speeding arrow. Not faster than a speeding bullet, but faster than a speeding arrow. This rider's dumb. What do you get? I'm going to do this too because I want this on my calculator. I'm going to guess it's a fairly big number because of those squareds. Oh. Did you get negative 1152670.5? Why negative? Losing energy. This number is big enough. I think I'm going to write it in scientific notation. 1, 2, 3, 4, 5. Yeah, I think I'm going to write negative 1.15 times 10 to the 6th joules. Where'd that energy go? It's got to go somewhere. That's what law of conservation of energy says. Where'd that energy go? Yeah. And again, this is why electric cars are so much more efficient. When electric cars slow down, where does most of the energy go? Recharging the batteries. As long as you can bleed off the kinetic energy, the car has to slow down. It's the law of the universe. It doesn't matter. It doesn't say you have to put it to heat. Why not reuse it and recapture it? Ooh, Eric, what's part C wanting me to find? Ooh, how do I calculate power? On your green sheet. That would be momentum, lowercase p. I'm glad you made that silly mistake, but it is a mistake. As I mentioned, we don't have enough letters to go around the English. Lowercase p is momentum, uppercase p is power, and here's a hint. It's going to be in the energy section, in the work section. How do I calculate power? Go further down the sheet. Find where it says W equals FD, and I bet you it's right next to it. Yeah. Eric, do we know how much work? Say yes. Yes. It's going to be, I'm going to chuck the negative because it's a power loss, but I'm not going to refer to that as negative. So it's going to be, I'm going to write 1.15 times 10 to the 6th, but I'm using my answer button. Do we know how long it took him to stop or slow down? Say no. Get your stopwatches, get your smartphones out, please, folks. I've rewound the video a bit. I'll tell you when to start timing. You'll hear the engine change as he starts to slow down, and then I'll tell you when to stop timing. So get your stopwatches ready. Start. Stop. How much time did you get? 16 seconds, 16.7. How much time did you get? 16. You look like you were texting, unless your stopwatch requires your thumb to move back and forth. Okay. How much time did you get? Are you lying? I think you are. Put your phone face down. You're not that important. How much time did you get? 16.7. You know what? Let's use, because we're doing really rough, let's use 16. So go answer button, divided by 16. Ignore the negative, because I know it's a power loss. And I get 72,042 watts. Yes? No? Okay. How many 60-watt light bulbs could this light up? Well, I think if I just take this number, I'm going to multiply it by -1 to make it positive. If I just take this number and divide it by 60, that's how many light bulbs this energy loss could have lit up. And I get 1,200 light bulbs. Are you starting to see why electric cars are so much more efficient? If you can recapture and store that energy, do that. It's not just because of less greenhouse gases. Even if they were giving out the same greenhouse gases as internal combustion engines, they'd still be giving out less because they're so much more efficient in recapturing the energy. We're going to skip example 4. What's your homework? You could do number 1. Number 2 is good. Number 3 is good. We're going to skip number 4, the graphing question. We're going to skip number 5. It's a graphing question. I think I'll skip number 6. It's a graph question. Probably skip number 7. Wait a minute, there is no number 7. Haha. You can skip 8, you can skip 9, you can skip 10. In other words, all you're going to do is number 1, number 2, and number 3. Put your pencils down, look up.